This is the B-2 Spirit stealth bomber. It weighs 160,000 pounds, spans 172 feet wingtip to wingtip, and on radar it looks like a large bird. That is not an accident of shape. It is the result of geometry, chemistry, and obsessive engineering working together to fool a physics problem that should be impossible to fool at this scale. Radar works on a principle so simple it predates aviation entirely. A transmitter sends out a pulse of electromagnetic energy. That energy travels outward at the speed of light, strikes an object, and bounces back toward the receiver. The time between transmission and return tells the operator how far away the object is. The strength of the return tells the operator roughly how large it is. The entire science of radar detection is built on that returned signal. The echo. Make the echo small enough, and the object effectively disappears. The engineering problem is that a 172-foot aircraft made of metal should produce an enormous echo. The B-2 produces almost none. Understanding how requires understanding what exactly determines the size of a radar return. The formal measure of an object's radar visibility is called radar cross-section, abbreviated RCS. It is expressed in square meters, but it does not measure physical area. It measures the effective area of a perfectly reflective sphere that would return the same amount of energy as the actual object. A large commercial airliner has an RCS of roughly 100 square meters, about the footprint of a small apartment. An F-16 fighter has an RCS of around 5 square meters. The B-2's RCS is classified, but estimates from open-source defense analysis place it between 0.001 and 0.1 square meters, roughly the return from a large metal marble or, at best estimates, a small bird. This is not a modest improvement over conventional aircraft. It is a difference of several orders of magnitude achieved on an airframe that is physically larger than most of what it is being compared against. 3 factors determine an object's radar cross-section: its shape, its surface materials, and its internal geometry. The B-2 addresses all 3 simultaneously, and the solution to each one creates engineering constraints that make the solution to the others harder. This is why stealth aircraft are not simply conventional aircraft with special paint applied afterward. The stealth properties have to be designed in from the beginning, because every structural decision affects the electromagnetic behavior of the finished aircraft, and those decisions cannot be easily undone. Shape is the first and most fundamental factor. When a radar wave strikes a flat surface, it reflects like light off a mirror. The energy bounces away at an angle equal and opposite to the angle of incidence. If that flat surface happens to be aimed back at the radar transmitter, the return is strong. If it is angled away, the energy reflects off in a different direction, and the receiver sees almost nothing. The problem with conventional aircraft is that they are covered in flat and curved surfaces oriented in many different directions, which means radar energy hitting the aircraft from almost any angle finds at least some surfaces that reflect it back toward the source. A fuselage is a cylinder. A cylinder reflects radar energy back toward the transmitter across a wide arc of approach angles. Wings meet fuselages at angles that create corner reflectors, geometric arrangements where energy bounces between 2 surfaces and returns almost directly back to the source regardless of approach angle, the way a retroreflector on a bicycle works. These are the features that make conventional aircraft visible. The B-2 eliminates these features through a design philosophy that was called faceting in early stealth development. Every surface on the aircraft is angled so that radar energy striking it deflects away from the transmitter rather than back toward it. The flying wing shape: no fuselage, no vertical tail, and no protruding engine nacelles means there are no large cylindrical surfaces and no fuselage wing junctions to create corner reflectors. The leading edge of the wing is swept at a consistent angle across the entire span, so radar energy striking it from the front deflects upward and away. The trailing edge has a distinctive double W notch shape that serves the same function from the rear. Even the engine inlets, which on a conventional aircraft would present a deep cylindrical cavity that traps radar energy and returns it strongly, are shaped and positioned to minimize forward sector return. The shape solution creates an immediate aerodynamic problem. An aircraft optimized for low radar cross-section is not naturally optimized for stable flight. The B-2's flying wing configuration, iron stripped of vertical stabilizers and designed with surfaces primarily to deflect radar rather than generate lift efficiently, is inherently unstable. Left to its own physics, it would depart controlled flight in seconds. Every B-2 flight is managed by a fly-by-wire flight control computer that makes thousands of small adjustments per second to keep the aircraft on its intended flight path. The pilot inputs a command and the computer figures out which combination of control surfaces achieves it without losing stability. The computer is not a convenience. It is a structural requirement. Without it, the aircraft cannot fly. Shape alone is not sufficient to make the B-2 disappear from radar. A perfectly shaped aircraft made of conventional aluminum would still reflect significant energy from surface imperfections, panel seams, and the inevitable geometric compromises required to build a functional aircraft rather than a pure electromagnetic sculpture. This is where materials enter the problem, specifically the radar-absorbent material that covers essentially every external surface of the aircraft. Radar-absorbent material, referred to universally as RAM, works on a different principle than shape management. Where shaping deflects radar energy away from the receiver, RAM converts it into something else entirely. The material contains particles, typically iron-ferrite compounds or carbon-based elements, that interact with incoming electromagnetic energy at the molecular level. When a radar wave penetrates the RAM coating, the alternating electromagnetic field causes the particles to vibrate. That vibration dissipates energy as heat. And the radar wave that entered the coating does not bounce back. It is absorbed, converted, and lost as a negligible amount of thermal energy distributed across the surface. The return that reaches the radar receiver is a fraction of what struck the aircraft. The physics of RAM absorption are frequency dependent. A coating optimized to absorb radar energy at one frequency is less effective at others. This matters because different radar systems operate at different frequencies. Early warning radars typically use lower frequencies with longer wavelengths, while targeting and fire control radars use higher frequencies with shorter wavelengths. The B-2's RAM formulation is a classified compound designed to perform across the range of frequencies the aircraft is most likely to encounter. But no material absorbs equally well across all frequencies. This is one reason stealth aircraft are not truly invisible on radar. They have reduced signatures, optimized against the most threatening systems they are designed to penetrate, with residual vulnerability at frequency ranges outside the primary design envelope. Very low-frequency radars of the type some nations have developed specifically to detect stealth aircraft can produce returns from the B-2 that higher-frequency systems cannot. The RAM coating on the B-2 is not a paint in the conventional sense. It is a composite material applied in multiple layers to a prepared surface, with each layer contributing to the absorption profile. So the outermost layer has to survive flight, temperatures that swing from negative 60 degrees Fahrenheit at cruise altitude to significant aerodynamic heating near the leading edges, rain, hail, bird strikes, and the mechanical stress of pressurization cycles. It also has to remain electromagnetically consistent. A surface that has been damaged, even slightly, scatters radar energy differently than an intact surface, and scattering is almost always worse for radar cross-section than either clean reflection or clean absorption. A chip or scratch that would be a cosmetic issue on a conventional aircraft is a radar signature event on the B-2. It creates what engineers call a scatterer, a point on the surface that sends radar energy in unpredictable directions, some of which will be back toward the receiver. The leading edges of the wing receive the most severe environmental exposure and produce the most radar risk when damaged. At the leading edge, radar energy arrives at close to perpendicular incidence, the worst possible geometry for deflection management. The RAM at the leading edge has to absorb what the shape cannot deflect, under the harshest physical conditions on the aircraft. The formulation used there is denser and more absorptive than the general surface coating, and it is also the most fragile. A rain shower at low altitude can erode the leading edge coating enough to require inspection and repair before the next mission. This is not a hypothetical maintenance concern. It is a routine operational reality for every B-2 that flies. Panel seams present a separate electromagnetic problem. Now, the B-2's skin is made of composite panels that meet at seams running across the surface in patterns dictated by structural and manufacturing requirements. A seam is a discontinuity, a place where the surface changes character abruptly. Discontinuities scatter radar energy. The solution is conductive tape applied over every seam, pressed flush with the surrounding surface to within tolerances measured in thousandths of an inch. The tape maintains electromagnetic continuity across the junction, preventing the seam from acting as a scatterer. A gap in the tape the width of a credit card is enough to increase the radar return from that section of the aircraft measurably. The tape has to be inspected before every mission, replaced when it lifts or tears, and applied with a precision that requires dedicated training and specialized tools. The maintenance burden that stealth imposes on the B-2 is not a side effect of the technology. It is intrinsic to it. An aircraft that achieves low radar cross-section through the precise geometric and chemical properties of its surface cannot maintain those properties passively. The surface degrades. The coatings wear. The tape lifts. The panels flex under aerodynamic load and the seams shift by fractions of millimeters. All of it has to be corrected before the aircraft can fly a mission where its stealth properties are operationally required. The maintenance technicians responsible for the B-2's low observable properties, the LO techs as they are called, work with tools and procedures that have no equivalent in conventional aircraft maintenance. The inspection process before a mission begins with a physical examination of every inch of the aircraft's exterior surface, conducted under specific lighting conditions that reveal surface anomalies invisible under normal illumination. Technicians look for chips, bubbles, lifted tape, rough patches, and variations in surface texture that indicate the coating has separated from the underlying structure. The leading edges are examined with particular attention. The engine inlets are inspected internally. The panel seams are checked across their entire length. When damage is found, and on an aircraft that has flown recently, damage is almost always found somewhere. The repair process follows procedures developed specifically for each type of coating and each location on the aircraft. And the damaged area is prepared by sanding with progressively finer abrasives, each grade removing the previous grade's scratches until the surface is smooth to the required tolerance. Too aggressive and the repair creates more radar surface variation than the original damage. Too gentle and the new material does not bond correctly to the prepared surface. The repair compound is mixed in small batches with a working time measured in minutes. The chemistry that makes it absorptive also makes it cure quickly, and material that has begun to cure cannot be reworked. It is applied in layers, each one cured at a controlled temperature before the next is added. The final surface is sanded flush, using tools that remove material in increments of thousandths of an inch, and checked against templates that define the allowable surface variation. The entire repair process for a significant area of coating can take longer than the flight that caused the damage. The B-2 fleet is based entirely at Whiteman Air Force Base in Missouri, a decision that was made partly for security reasons and partly because the hangars at Whiteman were built specifically to support the aircraft's maintenance requirements. The hangars are climate controlled to prevent temperature and humidity fluctuations that would affect the RAM coatings. The aircraft are returned to these hangars after every flight, regardless of where they land for refueling during a mission, because the maintenance that follows each flight cannot be performed in field conditions. A B-2 that lands at a forward base for hot pit refueling during a long mission receives fuel and returns to Whiteman for its post-flight inspection. But the operational concept assumes that stealth maintenance is a centralized precision activity, not something that can be done with field tools on a flight line in a combat theater. This centralization creates a strategic vulnerability that the Air Force has been aware of since the B-2 entered service. The entire operational fleet of 20 aircraft, 20 in total for the entire United States Air Force, is based at a single location. A successful strike on Whiteman Air Force Base during a conflict would eliminate the B-2's ability to conduct further operations. The Air Force's response to this concern involves dispersal procedures that would move aircraft to alternate bases under certain threat conditions, but the maintenance infrastructure cannot be dispersed as easily as the aircraft. Stealth capability requires stealth maintenance, and stealth maintenance requires the specialized facilities, tools, compounds, and trained personnel that are concentrated at Whiteman. The operational availability rate of the B-2, the percentage of the fleet that is ready to fly a mission on any given day, is classified, but former officials and defense analysts have consistently described it as significantly lower than conventional bomber aircraft. This is the fundamental trade-off of stealth technology at this level of performance. The B-2 can do things no other aircraft can do. It can penetrate air defense systems that would destroy anything else sent against them. It can deliver precision weapons against targets that are otherwise unreachable without ballistic missiles. The price of that capability is an aircraft that requires extraordinary effort to keep functional, that is based in a single location, and that exists in numbers so small that losses would be strategically significant in a way that losses of conventional aircraft are not. The geometry and materials that make the B-2 stealthy against radar also create constraints on everything else the aircraft does: how it is built, how it communicates, how it manages its own systems, and how it handles the physics of flight at the edges of its designed envelope. The exhaust from the B-2's 4 General Electric F118 engines presents a particular challenge. Jet exhaust is hot, and hot gas produces an infrared signature that heat-seeking sensors can detect at significant range. The exhaust also contains particles and chemicals that can create a visible contrail at certain altitudes and temperatures, a white line across the sky that negates the radar stealth completely. The B-2 manages the exhaust signature by mixing cool bypass air with the hot core exhaust before it exits the aircraft, reducing the temperature of the efflux and making the infrared signature smaller. The exhaust outlets are positioned on the upper surface of the wing, behind the engines, facing upward and backward. This placement means the hottest part of the exhaust stream is shielded from ground-based sensors by the aircraft's own body. An observer directly below the B-2 cannot see the exhaust outlets. A heat-seeking missile fired from below has a significantly degraded target to track. And the same upper surface exhaust placement that helps manage infrared signature creates a noise signature that is distinctive and recognizable. The B-2's engines are not quiet, but the sound is projected upward and backward rather than downward and forward. At cruise altitude, the acoustic signature reaching the ground is attenuated by distance and by the aircraft's own structure, acting as a partial barrier. This is not silence. A B-2 overhead is audible, but it is directionally managed in the same way the radar and infrared signatures are managed. Every physical emission the aircraft produces is treated as a potential detection vector and addressed in the design. Radio communications present a different version of the same problem. A transmitting radio antenna is a radar target. The electromagnetic energy it puts out can be detected by passive sensors that listen for transmissions rather than sending out their own pulses. An aircraft that maintains radar silence but transmits voice communications to its base is not stealthy against a listening adversary. The B-2 manages this by operating in a communications-minimized mode during the penetration phase of a mission, the segment where stealth matters most. The aircraft receives information through low probability of intercept data links that use spread spectrum techniques to make the transmission difficult to detect or locate. It transmits as little as possible. The crew is trained to regard any outbound emission as a potential compromise of the mission. The question of what happens when stealth fails, when the B-2 is detected despite everything, points to a layer of the aircraft's design that is rarely discussed in the context of stealth specifically. The B-2 has no defensive weapons. It carries no missiles for self-defense, no jamming systems of the active variety used by dedicated electronic warfare aircraft. Its defense is not being found. If it is found and engaged by a capable air defense system, its options are limited to evasive maneuvering and the aerodynamic performance of an aircraft that was not designed primarily for maneuverability. The flying wing configuration that contributes to its low radar cross-section also limits the aggressive maneuvering that a conventional fighter can perform. The B-2 can turn and descend and climb. But it cannot outfly a missile in the way a dedicated fighter might attempt to. The stealth is not a supplement to conventional defensive capability. It is a replacement for it. The design assumes the aircraft will not be found. Everything downstream of that assumption, combat persistence, escape options, crew survival, depends on that assumption holding. The B-2's radar cross-section will not remain the state-of-the-art indefinitely. Radar technology has advanced since the B-2 was designed in the 1980s, and the specific frequency ranges and waveforms against which the aircraft was optimized are not the only ones that modern air defense systems can use. Low-frequency radars, multi-static radar networks that use separated transmitters and receivers to defeat the angular management of reflected energy. And passive detection systems that listen for the aircraft's own emissions rather than sending out pulses. All of these present challenges to stealth designs optimized against a specific threat environment. The Air Force's answer to this evolution is the B-21 Raider, currently entering service as the B-2's eventual replacement. The B-21's specific stealth characteristics are classified, but the design incorporates advances in materials science, manufacturing precision, and low observable engineering developed in the decades since the B-2 was built. The same physics apply, the same trade-offs apply. The difference is that those trade-offs are now being managed with 40 years of additional knowledge about what radar can do and what geometry and chemistry can do in response. The B-2 remains, for now, and been the most capable penetrating bomber in the world. Its ability to reach targets that no other aircraft can reach without suffering destruction is real and operationally demonstrated. That capability rests entirely on a surface, on the precise geometry of every panel, the intact chemistry of every coating, the flush alignment of every seam that is more fragile than the aircraft's reputation suggests and more carefully maintained than most people who discuss the aircraft ever consider. The bomber that disappears from radar disappears because hundreds of people on the ground work continuously to keep it that way. Without them, it is a very expensive shape with no particular advantage over anything else in the sky. Else in the sky. Else in the sky.